The electric sun hypothesis. The basics. In this day and age, there is no longer any doubt that electric effects in plasmas play an important role in the phenomena we observe on the sun. The major properties of the electric sun ES model are as follows. Most of the space within our galaxy is occupied by plasma, rarefied ionized gas, containing electrons, negative charges, and ionized atoms, positive charges. Every charged particle in the plasma has an electric potential energy, voltage, just as every pebble on a mountain has a mechanical potential energy with respect to sea level. The sun is at the center of a plasma cell, called the heliosphere, that stretches far out, several times the radius of Pluto. As of 9/9/2012, the radius of this plasma cell has been measured to be greater than 18 billion kilometers, or 122 times the distance from the sun to Earth. These are facts, not hypotheses. The sun is at a more positive electrical potential, voltage, than is the space plasma surrounding it, probably in the order of several thousand volts. Positive ions leave the sun, electrons enter the sun. Both of these flows add to form a net positive current flowing through the sun, entering at the poles and leaving radially at lower latitudes. This constitutes a plasma discharge, analogous in every way, except size, to those that have been observed in electrical plasma laboratories for decades. Because of the sun's positive charge, voltage, it acts as the anode in a plasma discharge. As such, it exhibits many of the phenomena observed in earthbound plasma laboratory experiments. The sun may be powered not from within itself, but from outside, by the electric Birkeland currents that flow in our arm of our galaxy, as they do in all galaxies. This possibility that the sun may be externally powered by its galactic environment is the most speculative idea in the ES hypothesis, and is always attacked by critics, while they completely ignore all the other obvious properties of the ES model. In the plasma universe is high. An electrically powered sun's radiated power would be due to the energy delivered by that amperage. As it travels around the galactic center, the sun may come into regions of higher or lower current density, and so its output may vary, both periodically and randomly. The corona. The sun's corona is visible only during solar eclipses, or via sophisticated instruments developed for that specific purpose. It is a vast, luminous plasma globe that changes shape with time, always remaining fairly smooth and distributed in its inner regions, and showing filamentary spikes and points in its outer fringes. It is a glow-mode plasma discharge. If the sun were not electrical in nature, this corona would not exist. If the sun is simply a non-electrical nuclear furnace, the corona has no business being there at all. So one of the most basic questions that ought to arise in any discussion of the sun is, why does our sun have a corona? Why is it there? It serves no purpose in a fusion-only model, nor can such models explain its existence. The solar wind. Positive ions stream outward from the sun's surface and accelerate away through the corona for as far as we have been able to measure. It is thought that these particles eventually make up a portion of the cosmic ray flux that permeates the cosmos. The wind varies with time and has even been observed to stop completely for a period of a day or two. What causes this fluctuation? The ES model proposes a simple explanation. and suggests a mechanism that both creates and controls fluctuations in its flow. The standard model provides no such explanation or mechanism. See solar surface transistor action, electrical properties of the photosphere and the chromosphere. The essence of the electric sun hypothesis is a description of the electrical properties of its photosphere, chromosphere, and the resulting effects on the charged particles that move through those layers. The surface of the sun that we typically see from Earth is the photosphere, which is a brightly radiating layer of plasma only about 500 kilometers thick. It is analogous to the anode glow region of a laboratory gas discharge experiment, except that it is in arc mode. It consists of cells of plasma, sometimes called tufts or granules. Sunspots are areas where no such granules exist. The granules observed on the surface of the photosphere are in fairly turbulent motion. They change shape, size, and disappear in a matter of hours or days. New ones pop up in their place. The anode glow is often observed in the laboratory to consist of a pattern of small, rotating, regularly arranged spots whose speed of rotation is sometimes sufficiently slow to be followed by the unaided eye. The analogy between the laboratory gas discharge and the behavior of the sun is indeed a compelling one. The photosphere then is plasma in the arc mode. We say this because the sun emits power at a rate of over 63 million watts per square meter from its photospheric surface. This is equivalent to a power output of 40 kilowatts from each square inch of that surface. Some have questioned whether the photosphere's relatively low temperature, about 5,800 Kelvin, disqualifies it from being in arc mode. In 1944, C.E.R. Bruce of England's Electrical Research Institute proposed that the photosphere has the appearance, the temperature, and the spectrum of an electric arc. It has arc characteristics because it is an electric arc, or a large number of arcs in parallel, and it is difficult to imagine a plasma discharge in anything other than arc mode that could radiate 40 kilowatts of power from each square inch of its surface area. A cross-section taken from a photospheric granule is shown in the three plots shown together below in Figure 1. The horizontal axis is distance, measured radially outward, upward, starting at a point near the bottom of the photosphere, the true surface of the sun, which we can only observe in the umbra of sunspots. Almost every observed property of the sun can be explained through reference to these three plots. For this reason, much of the discussion that follows makes reference to them. The first plot shows the energy per unit positive charge of an ion as a function of its distance out from, altitude up from, the solar surface. The units of energy per unit charge are volts, V. The second plot, the E field, shows the outward-upward radial force toward the right in this figure, experienced by each such positive ion. The third plot shows the locations of the charge densities that will produce the first two plots. The chromosphere is the location of a plasma double layer, DL, of electrical charge. Recall that one of the properties of electric plasma is its excellent, although not perfect, conductivity. Such an excellent conductor will support only a weak electric field. Notice in the second plot that the almost ideal plasmas of the photosphere, region B to C, and the corona from point E outward are regions of almost zero electric field strength. End of part 1. When we consider the Sun, however, spherical geometry exists, with the Sun at the center. The cross-section becomes an imaginary sphere. Assume a constant total electron drift moving from all directions toward the Sun, and a constant total radial flow of positive ions outward. Imagine a spherical surface of large radius through which this total current passes. As we approach the Sun from deep space, this spherical surface has an ever-decreasing area. Therefore, for a fixed total current, the current density, A over m squared, increases as we move inward toward the Sun. The anode surface of the Sun is a tiny fraction of the area of the virtual cathode, the area of the heliopause. According to the latest measurements, the surface area of the heliopause is 653 million times larger than the surface area of the Sun. Thus, current density at the Sun's surface will be 653 million times what it is at the heliopause cathode. In deep space, say just inside the heliopause, the current density there is extremely low, even though the current may be huge. We are in the dark current region. There are no glowing gases. Nothing to tell us we are in a plasma discharge, except possibly some radio frequency emissions. As we get closer to the Sun, the spherical boundary has a smaller, decreasing surface area. The current density increases. We enter the normal glow region. This is what we call the Sun's outer corona. The intensity of the radiated light is much like a neon sign. The volt-ampere plot has negative slope, and so filaments form. Filaments are often clearly observed in the outer corona. Those filaments may indeed be Berkeley currents. As we approach still closer to the Sun, the spherical boundary gets to be only slightly larger of the radiated light. It is much like an arc welding machine or a motion picture projector. A high-intensity ultraviolet light is emitted. It is well known that if the anode in a discharge is much smaller than the cathode, and the photosphere exists on the Sun, the boundary between the corona, glow mode, plasma, and the photosphere, arc mode, is a double layer, DL. This phenomenon is often observed in laboratory plasma experiments. Some early plasma researchers and most modern astronomers believe that the only true plasma is one that is perfectly conductive and so will freeze magnetic fields into itself. This is the erroneous theoretical basis of magnetic reconnection. The volt-ampere plot shown above indicates that this does not happen. Every point on the plot, except the origin, obviously the static resistivity of a plasma in the high zero static resistivity, it has a non-zero static resistivity. It takes a non-zero E field to produce the current density. Obviously, the static resistivity of a plasma in the high end of the dark mode can be quite large. The arc region and the left half of the glow region exhibit negative dynamic resistance, and the E field can be quite small. But that is not what is in question. No real plasma can freeze in a magnetic field. The highest conductivity plasmas are those in the arc mode. But even in that mode, it takes a finite non-zero valued electric field to produce current density. No plasma is an ideal superconductor. Figure 1 energy, electric field strength, and charge density as a function of radial distance from the sun's surface. The energy plot shown above in the photo is valid for positively charged particles because a positive E field represents an outward radial force toward the right per unit charge on any such particle. The region wherein the E field is negative A to B constitutes an inward force. This region of the lower photosphere is thus an energy barrier that positive ions must surmount in order to escape the body of the sun. Any ions attempting to escape outward from within the sun must have enough energy to get over this energy barrier. So the presence of this single positive charge layer at the bottom of the photospheric plasma serves as a constraint on unlimited escape of ions on the surface of the sun. Granule shrinkage and movement. In order to visualize the effect this energy diagram has on electron, negative charges coming in toward the sun from cosmic space from the right, we can turn the energy plot upside down. Doing this enables us to visualize the trap that these photospheric granules are for incoming electrons. As the trap fills, the energy of the granule existing between B and C decreases in height, and so the granule weakens, shrinks, and eventually disappears. This is the cause of the observed shrinkage and disappearance of the photospheric granule. Temperature minimum. If the standard model were correct, heat and light would simply radiate away from the photosphere as from a hot stove. Temperature measurements would monotonically decrease with distance. But many processes, other than simple radiation of heat, are occurring above the photosphere. A temperature minimum of about 4100 Kelvin occurs just above the photosphere, the lower region of the sun's corona. At much higher altitude are millions of degrees hotter than the surface of the sun itself. How can this be? The standard model has no satisfactory explanation. The electric sun hypothesis explains it clearly as follows. Charged particles do not experience external electrostatic forces when they are in the range B to C within the photosphere. Only random thermal movement occurs due to diffusion. Temperature is simply the measurement of the violence of such random movement. This is where the about 6,000 Kelvin photospheric temperature is measured. Positive ions have their maximum electrical potential energy when they are in this photospheric granule plasma, but their mechanical kinetic energy is relatively low. At a point just to the left of point C, any random movement toward the right, radially upward, that carries a positive ion, even slightly beyond point C, will result in its being swept away, down the energy hill, out of the sun. Such movement of charged particles due to an E field is called a drift current. This drift current of accelerating positive ions is a constituent of the solar wind, which is a serious misnomer. As positive ions begin to accelerate down the potential energy drop from point C through point E, they convert the high electrical potential energy they had in the photosphere into kinetic energy. They gain extremely high outward radial velocity and lose side-to-side random motion. Thus, they become dethermalized. In this region, in the upper photosphere and the chromosphere, the movement of these ions becomes extremely organized, parallel. Therefore, an observed temperature minimum occurs here. The transition zone. Rapidly moving positive ions past point E, they leave the chromosphere. They move beyond the radial outward directed E-field force that has been accelerating them. Because of their high kinetic energy velocity, any collisions they have at this point with other ions or neutral atoms are violent and create high amplitude random motion, thereby rethermalizing the plasma to a much greater degree than it was in the photospheric granule. This is what is responsible for the high temperature we observe in the lower corona. Ions just to the right of point E are reported to be at temperatures of 1 to 2 million Kelvin. Nothing else but exactly this kind of mechanism could be expected from the electric sun photospheric double-layer model. The rethermalization takes place in a region analogous to the turbulent white water boiling at the bottom of a smooth laminar water slide. In the fusion model, no such accelerating water slide mechanism exists, and so neither does a simple explanation of the temperature discontinuity. Cosmic rays. The particles in our solar wind eventually join with the spent solar winds of all the other stars in our galaxy to make up the total cosmic ray flux in our arm of the galaxy. Jurgens points out that the Sun is a rather mediocre star as far as radiating energy goes. If it is electrically powered, perhaps its mediocrity is attributed to a relatively unimpressive driving potential. This would mean that hotter, more luminous stars should have driving potentials greater than that of the Sun, and should consequently expel cosmic rays of greater energies than solar cosmic rays. A star with a driving potential of 20 billion volts would expel protons energetic enough to reach the Sun's surface, consequently expel cosmic rays of greater energies than solar cosmic rays, arriving with 10 billion electron volts of energy to spare. Such cosmic ions, when they collide with Earth's upper atmosphere, release the muon neutrinos.
Muon neutrinos.
That have been in the news recently. Hans Alfvén, in his book The New Astronomy, Chapter 2, Section 3, page 74 to 79, said about cosmic rays, how these particles are driven to their fantastic energies, sometimes as high as 1,000,000 billion electron volts, is one of the prime puzzles of astronomy. No known, or even unknown, nuclear reaction could account for the firing of particles of such energies. Even the complete annihilation of a proton would not yield more than 1 billion electron volts. Fluctuations in the solar wind. It is interesting to note in passing that the 3 plots presented in Figure 1 are identically the plots of energy, E-field, and charge distribution found in a junction transistor. Of course, in that solid-state device, there are different processes going on at different energy levels. Valence band and conduction band. Within a solid crystal, in the solar plasma, there are no fixed atomic centers, and so there is only one energy band. In a transistor, the amplitude of the collector current, analogous to the drift of positive ions in the solar wind toward the right, is easily controlled by raising and lowering the difference between the base and emitter voltages. Is the same mechanism a voltage fluctuation between the anode sun and its photosphere granules at work in the sun? E.g., if the sun's voltage were to decrease slightly, say because of an excessive flow of outgoing positive ions, negative, the voltage rise from point A to point B in the energy diagram would increase in height and so reduce the solar wind, both the inward electron flow and the outward positive ion flow, in a compensating negative feedback effect. In May of 1999, the solar wind completely cut off for about 2 days. There are also periodic variations in the solar wind. The transistor-like mechanism described above is certainly capable of causing these phenomena. The fusion model is at a complete loss to explain them, whereas transistor cutoff is a well-known electronic mechanism that is used in all digital circuits. Characteristic modes of plasma. In the page on electric plasma on this website, the 3 characteristic static modes in which a plasma can operate are discussed. Here is a somewhat more exact description. We need this to explain the detailed properties we observe on the sun's surface. The static volt-ampere characteristic of a typical laboratory plasma discharge inside a cylindrical chamber has the shape shown below in the current picture. So the sun acts like a transistor. That's interesting. And crystals are in transistors. Fusion in the double layer. The Z-pinch effect of high-intensity parallel current filaments in an arc plasma is very strong. Whatever nuclear fusion is taking place on the sun is probably occurring here in the double layer, DL, at the top of the photosphere, not deep within the core. The result of this fusion process are the metals that give rise to absorption lines in the sun's spectrum. Traces of 68 of the 92 natural elements are found in the sun's atmosphere. Most of the radio frequency noise emitted by the sun emanates from this region. Radio noise is a well-known property of double layers. The electrical power available to be delivered to the plasma at any point is the product of the E field, V over M, times current density, A over M to the second. This multiplication operation yields watts per cubic meter, power density. The current density is relatively constant over the height of the photospheric chromospheric layers. However, the E field is at its strongest at the center of the double layer. Present thinking is that nuclear fusion takes a great deal of power. If that is so, then the power is available in the double layer. It has reportedly been observed the neutrino flux from the sun varies inversely with sunspot number. This is expected in the ES hypothesis because the source of those neutrinos is probably Z-pinch produced fusion, which is occurring in the double layer. And sunspots are locations where there is no double layer in which this process can occur. The greater the number of sunspots, the fewer the number of observed solar neutrinos. Sunspots. In the plasma of the photosphere, both the dimensions of and the voltage within the granules depend on the current density at that location near the sun's anode surface. The existence of the double layer of electric charge associated with each granule, separating it from the corona plasma above it, requires a certain numerical relationship between positive ion and electron numbers in the total current. This required ratio of electron to ion motion was discovered, quantified, and reported by Irving Langmuir over 50 years ago. Spicules, tall jets of electrons that emanate from the boundaries between the granules, supply many of those needed electrons. In this electric sun model, as with any plasma discharge, the granular cells disappear wherever the flux of incoming electrons impinging into a given area of the sun's anode surface is not sufficiently strong to require the augmentation of anode size they provide. At any such location, the photospheric cells collapse, as we can see down the actual anode surface of the sun. Since there is no arc mode plasma discharge occurring in these locations, they appear darker than the surrounding area and are termed sunspot umbrae. Of course, if a tremendous amount of energy were actually being produced in the sun's interior, these umbrae should be brighter and hotter than the surrounding photosphere. The fact that sunspot umbrae are dark and relatively cool, 3 to 4,000 Kelvin or 2727 to 4227 Celsius, strongly supports the condition that very little, if anything, in the way of heat production is going on in the sun's interior. The Sun, Part 3. Figure 3, a sunspot showing the umbra, penumbra, and surrounding granular cells. The top plot in Figure 1 shows the electrical potential energy of a positive ion in the Sun's atmosphere. This diagram is expanded and reproduced below in Figure 4 and is relabeled to show the energies, voltage levels, at different locations in the vicinity of a sunspot. In Figure 3, normal bright yellow arc mode solar granules appear around the periphery of a typical sunspot. They are at voltage level 1/2 in Figure 4. Typically, in these normal granules, positive ions flow upward, directly out toward the viewer in Figure 3. In Figure 4, such ions have enough energy to make the journey from the interior of the Sun, left of the origin, marked as A on the horizontal axis, up over the voltage rise from A to B. They diffuse across the region B to C and fall down the potential hill from C to E. At this point, these rapidly moving ions create the turbulence observed as the high 2 million Kelvin temperatures seen in the lower corona. In Figure 3, this journey takes such an ion up out of the Sun's interior, up through a granule, and accelerates it out vertically upward. These ions then continue outward as the major constituent of what is called the solar wind. We must be aware of what Figure 4 represents. The black locus indicates a voltage A positive ion would experience along its journey upward out of the Sun's body through the photospheric granule and upward into the lower corona. Penumbral filaments. But what about the penumbra, those strangely shaped plasma filaments, cells surrounding the umbra, that remind us of the iris of a human eye? Starting just inside the Sun's body, some ions have barely enough kinetic energy to leave the body of the Sun by rising up to voltage level V2 or greater. In the altitude range B to C in Figure 4, where they are diffusing upward, some of these ions may collide with other ions, or neutral atoms, and some of them may be given a diffusion velocity that bounces them back downward toward the left in Figure 4. If they diffuse in the direction beyond point B, they will be attracted back down into the Sun. In 3D space, they may just sink out the bottom of the granule, or fall off its side into the darker channels that surround each granule. Or, if they are close enough to the edge of a sunspot, they may fall into it. That is what we are seeing in the penumbral filaments shown in Figures 3 and 5. The process is analogous to icebergs calving off from glaciers to which they have been attached. The tops of the granules near the umbra's edge peel off, bend downward toward the umbra, and fall toward the lower voltage and lower altitude surface of the Sun, visible in the umbra. Yeah, it's interesting. The interior of the Sun is obviously rocky. Prominences, flares, and CMEs. All of the above discussion applies to the steady state, or almost steady state, operation of the electric sun. There are several dynamic phenomena such as flares, prominences, and coronal mass ejections, CMEs, that we observe. How are they produced? Nobel laureate Hans Alfvén, although not aware of the Jurgen's electric sun model, advanced his own theory of how prominences and solar flares are formed electrically. It is completely consistent with the Jurgen's model. Any electric current, I, creates a magnetic field. The stronger the current, the stronger the magnetic field, and the more energy it contains. Curved magnetic fields cannot exist without either electrical currents or time-varying electric fields. Energy, Wm, stored in any magnetic field is given by the expression Wm equals
1/2 Li squared.
1/2 Li squared. If the current I is interpreted, the field collapses and its energy must be delivered somewhere. The magnetic field of the Sun sometimes, and in some places on its surface, forms an omega-shaped loop. This loop extends out through the double sheath layer, DL, of the chromosphere. I need a drink of water. One of the primary properties of Birkeland currents is that they generally follow magnetic field lines. A strong looping current will produce a secondary toroidal magnetic field that will surround and try to expand the loop. If the current following the loop becomes too strong, the double layer will be destroyed. This interrupts the current, like opening the switch in an inductive circuit, and the energy stored in the primary magnetic field is explosively released into space. It should be well understood, certainly by anyone who has had a basic physics course, that the magnetic field lines that are drawn to describe a magnetic field have no beginning nor end. They are closed paths. In fact, one of Maxwell's famous equation is
DIVB equals 0.
DIVB equals 0. Which says exactly that in the language of vector differential calculus. So when magnetic fields collapse due to the interruption of the currents, they produce them. They do not break or merge or recombine, as some uninformed astronomers have postulated. The field simply collapses very quickly on the Sun. This collapse can release a tremendous amount of energy, and matter is thrown away from the surface. As with any explosively rapid reaction, this release is consistent with and predicted by the electric sun model as described above. That is how coronal mass ejections, CMEs, occur. Note that although astronomers ought to be aware that magnetic fields require electrical currents, or time-varying E-fields, to produce them, currents and E-fields are almost never mentioned in standard models. Conclusion. This rather lengthy page has actually been the briefest of introductions to Jurgen's electric sun model. The realization that our sun functions electrically, that it is a huge electrically charged, relatively quiescent sphere of ionized gas that supports an electric plasma arc discharge on its surface, and is probably powered by subtle currents that move throughout the now well-known tenuous plasma that fills our galaxy. A more detailed description of the ES hypothesis, as well as the deficiencies of the standard solar fusion model, are presented in The Electric Sky. Today's orthodox thermonuclear model fails to explain many observed solar phenomena. The electric sun model is inherently predictive of most, if not all, these observed phenomena. It is relatively simple, it is self-consistent, and it does not require the existence of mysterious entities such as the unseen solar dynamo genie that lurks somewhere beneath the surface of the fusion model and serves as a fallback explanation for all observations that are inconvenient for the accepted fusion model. Ralph Jurgens had the genius to develop the electric sun model back in the 1970s. He based it on the work of others who went before him. His hypothesis and modern extensions of it have so far passed the harsh test of observed reality. They have passed several tests to which the Sapphire Laboratory team have subjected it. This seminal work may eventually get the recognition it deserves. Or, of course, others may try to claim it or parts of it and hope the world forgets who came up with these ideas first. There is now enough inescapable evidence that a majority of the phenomena we observe on the sun are fundamentally electric in nature. Ralph Jurgens had the vision to recognize that. Don Scott.